Thank you, everybody, for coming. My name is Matt Duffler. I'm a software engineer for Google out of New York. I'm here today with Andy Glover, an engineering manager for Netflix, and we're here to talk to you about Spinnaker. Spinnaker is a recently released open source continuous delivery platform. It supports multiple cloud platforms out of the box, including comprehensive support for Google Compute Engine. So before we dive into the particulars of Spinnaker itself, let's talk a bit about the problem we're trying to solve. And that is managing the complexity of cloud deployments in cloud environments. Make no mistake about it, cloud deployments are complicated. We talk to customers quite often, and one thing we hear constantly is that they'd like to increase developer velocity. What this amounts to is dealing with the volume of change. In terms of increasing developer velocity, the key is to reduce the friction and time between developers making changes and those changes landing in production. There are many developers changing systems all the time, pushing these changes, and this is only going up over time. As organizations add developers, the volume of change increases. We try to reduce friction and time as these changes are pushed to various stages into production. In addition, you have multiple services being deployed independently. Organizations are moving to a microservices model, and as these services are deployed, you have potentially an exponential number of changes being pushed into production, an exponentially increasing number of changes. In an ideal world, changes to these services as they're rolled out are isolated from one another through a robust set of APIs. Still, this increases complexity. The volume of change is always increasing. There are always more services coming online. Also keep in mind it's not a static world. Things are always changing. You're typically deploying to cloud environments that are being dynamically scaled, and the days when you could turn off your service to do upgrades or make changes are long gone. So you need to be able to gracefully roll out your changes while you're continuing to service your users, while your cloud footprint may be scaling in response to load. And lastly, you need to be able to revert changes. If something goes wrong as you do these rollouts, you need to be able to gracefully and quickly roll back before you do damage to your business. So how do we handle this complexity? It's a combination of principles, practices, and tools. The key principle is immutable infrastructure. Andy's going to come up in a minute, and he's going to tell you about how they employ this principle at Netflix using this tool Spinnaker, which we're going to go into a lot of detail and show demos. But first, let's talk about immutable infrastructure a bit. So the way things work, you typically have a machine. It has CPU resources, memory, disk. Some of this is virtual, some potentially real. You have that machine layer. On top of that, you have an operating system layer. You have whatever libraries and applications your application depends on, typically something like an app or a web server. And then you have your actual application. And each of these different layers can be deployed onto these machines using different tools. Before cloud computing really went mainstream, you would typically use something like a config management system. You would use that to manage your web and app server, and then maybe another specialized tool to deploy your application. When you would roll out changes, you would connect to those running machines and redeploy the application with the changes onto that running system. With the advent of cloud computing and companies moving to an immutable infrastructure model, you would never do this. The idea is that in the old days, when it was expensive and slow to build new machines, you tried to avoid building new machines from scratch. Now that it's fast and cheap to roll out new machines, you're provisioning new machines all the time in the cloud. So tearing down a machine, provisioning a new machine, installing all of your software, this is fast and cheap and easy now. So when you roll out a new version of your software, instead of modifying things in place, which is risky, you take the approach where I have my new version of software, let me bake a static machine image with that software, let me move that image into a test cluster, let me run my tests against it. Once I'm happy, I stop traffic from reaching the old version, traffic's only reaching the new version, and later on, you can go off and gracefully destroy that old infrastructure. Anything goes wrong along the way, you can easily roll back. Just direct traffic back to that old cluster. So at Google, we have tens of thousands of developers. It's 30,000 plus developers changing things all the time. We have a principle where any developer can change any part of the code base. We have something like a Linux kernel's worth of changes landing in production weekly. So how do we manage all this change? Well, we bake new images, we manage traffic, we don't modify systems in place. Other companies following these same principles, companies like Netflix, have been applying the concepts of immutable infrastructure. It's been working very well for them. The majority of their deployments are done employing immutable infrastructure. And the tool they use primarily to make this happen is Spinnaker. This is their flagship tool. It's a centerpiece of their cloud platform. And Andy's going to come up and tell us quite a bit about it now, and then I'll come back up and do some demos. There you go.
Thank you, Matt. Thanks a lot. It's great to be here. Is everyone warm enough? I'm freezing. So Jez Humble, who wrote a seminal book on continuous delivery, captures what I think is the essence of continuous delivery. And that's about making deployments boring. No longer are they cross-functional, scheduled events that require a whole lot of people to get in the same room and figure out what's going on. They're just simply done, and they're done reliably. And the businesses that are seeing are taking advantage of continuous delivery are obviously seeing accelerated time to market. They can produce products quickly and get them in front of customers quickly. And because they can do that, they turn out to build the right product. They're not waiting a long time to figure out whether or not this product actually is a viable thing for users. By delivering the right product quickly, they're seeing increased customer satisfaction, and they're delivering a product that's of higher quality. And so continuous delivery isn't new to Netflix. We've been doing it a long time. And in fact, we see continuous delivery as the facilitator for innovation at Netflix. We went to the cloud 6 years ago and immediately saw that we needed to start building some tooling so that we could start pushing out software quickly to you all. And we started with a tool called Asgard. And Asgard, in many ways, captured the cloud model for Netflix and maybe the industry in general, in terms of there's the notion of an application, and an application has clusters, and clusters are made up of auto-scaling groups or server groups. Asgard served us well and served many other companies well as well. And we did, though, see that Asgard lacked some of the real continuous delivery features that we needed, so we embarked on another effort, and that effort was called Mimir. And Mimir added the notion of pipelines in front of Asgard, and thus created a bit more velocity with respect to how we were doing deployments. Around the same time Mimir was built, there was yet another continuous delivery platform built called Edge Center, which the Netflix Edge platform team had built. And this was also highly successful in terms of rolling out production software to the edge of the Netflix architecture. So continuous delivery isn't new to Netflix. We've been doing this a long time. We've learned a heck of a lot of lessons. We sure know how not to do it, and we think we're pretty good at knowing how to do it. And so about a year and a half ago, we embarked on a new effort to create an entirely new platform from the ground up called Spinnaker. And Spinnaker is a hardened continuous delivery platform built to be tier 0 for the business of delivering software. As I said, it's leveraged the lessons we've been learning for quite a long time about how to move quickly into the AWS cloud. We open sourced Spinnaker late last November, and Spinnaker itself is ultimately a workflow tool. It has the notion of pipelines. Pipelines are made up of stages. After you deploy an asset to some endpoint, you also have the ability to manage those assets. And Spinnaker itself integrates deeply with other operational systems that can support telemetry, testing, and performance monitoring, for example. And Spinnaker has been built in partnership with a number of companies, including Google, Microsoft, Pivotal, and Kenzan. And these partnerships reflect a deep integration with various systems, i.e. Google Cloud Platform, Microsoft Azure, Pivotal Cloud Foundry. And these partnerships have been bidirectional from the standpoint of we're learning from Google, we're learning from Azure, and hopefully vice versa, they're learning something from us. And pluggability is key to Spinnaker. Not only are the assets that you can deploy with Spinnaker pluggable, Netflix has a very long history of deploying AMIs, virtual images, virtual machine images. But we want to be able to deploy other things. Stages of pipelines, they themselves are also pluggable. We have our own set of stages internal to Netflix. Some of them are open source, some of them aren't. Ostensibly, other companies will create stages that are unique to their environment. And ultimately, the whole notion of cloud providers themselves are pluggable. And this pluggability is key for Netflix. We want to leverage all of AWS. Previous tooling was very much centered around EC2 compute. We want to take advantage of other services at AWS like ECS, S3, CloudFront, Lambda. All of AWS is a fertile ground for Netflix deployments, and we want our tooling to support it natively. We also want to take advantage of CDN deployments. Obviously, Netflix has a very, very large CDN presence, and we want Spinnaker to handle the deployments to Akamai. JARs, libs, there are plenty of teams that their end asset necessarily isn't a service that facilitates watching video, but it could be some library that facilitates it some other way. We want to be able to support deploying that library into like Artifactory, for example. And then last but not least, the system needs to be flexible enough to handle the coming tidal wave of containers. And the good news is that Spinnaker supports all of these through a pluggable model. As I said, we began Spinnaker about a year and a half ago. It's in production today at Netflix. And the success of Spinnaker is predicated on that it's a self-service platform. It's got a super easy-to-use UI, which you'll see, that teams can go in and figure out how to start using it immediately. They don't need training. They don't need some document or manual. The ability for teams to fashion their own delivery pipelines. There is no standard pipeline at Netflix. There's a tool, obviously Spinnaker, that allows you to create pipelines with various stages, but the stages that a team decides to build is entirely up to that team. So a wide breadth of pipelines. And then last but not least, because Spinnaker is open source, we get to take advantage of some of the innovations that you all are building in your companies for your needs. And we've seen that already today in that pull requests are coming in and Netflix is taking advantage of that. So it's definitely a bi-directional relationship, and that's why we choose the open source software. Today, Spinnaker is doing 4,000 deployments a day. Netflix has roughly 24 AWS accounts, with a dozen being accounts that are important for streaming video. Because we have a standard platform, people can plug into it easily. It has a flexibility with pipelines. More and more teams are creating pipelines day in and day out, and that's leading to a skyrocketing number. In fact, before I made this presentation, I thought the number was 2,000, and then our data science people actually corrected me and said, no, it's actually at 4,000. So we've seen a tremendous growth in deployments to AWS within Netflix since releasing Spinnaker. And the beauty of this pluggable, yes, there it is. The beauty of this standard platform that's pluggable is that everyone at Netflix benefits from Spinnaker. When new tools get online, the first thing they do is they integrate with Spinnaker. And then all teams at Netflix get advantage of it. So case in point, we have a sophisticated, I don't have enough coffee and it's freezing, so that's my excuse. We have a sophisticated automated canary analysis framework. That team plugged it into Spinnaker. It's a custom stage. And now everyone at Netflix gets to take advantage of ACA, a sophisticated form of testing before you go live. Another case in point, Netflix has a container cloud called Titus for obviously running containers. That's plugged into Spinnaker. Now all teams at Netflix can leverage Titus for deployments should they choose to do so. And as new tools and services are built at Netflix, those teams are plugging them into Spinnaker, and all teams at Netflix, again, get to leverage that innovation. So I said it was a beautiful UI, and it's easy to use. And again, Matt will give more details, but it's a phenomenal UI. It's awesome. And as I said, it allows you to manage assets in production. So there's this notion of a cluster. A cluster spans the globe. And then you have server groups, or ASGs, inside of a cluster. In this case, here's a server group that's it's in US East in Amazon, and then there's US West. We codify deployment patterns. Again, that umbrella of innovation. Red-black deployments, which the rest of the world calls blue-green. All teams get to take advantage of these sophisticated deployment strategies within Spinnaker. Pipelines. This is the pipeline screen. This is a pipeline execution that shows a series of stages that ultimately culminates in a deployment into production. Spinnaker supports parallel stages, so you can obviously run things in parallel. You can deploy to many regions at once if you choose to. You have deployment windows, so you can elect to say, I want to deploy this particular asset at this part of the globe at this time of the day. All in all, it's a very flexible, pluggable system, and it's seen phenomenal success. I'm having a hard time here. Success at Netflix. And so I'd like to transition it back to Matt. Netflix and Google have been working together on Spinnaker for about a year. And as I say, the innovation is going both ways. I'm going to assume you guys have learned something from us.
We hope so.
And we've definitely learned something from the Google folks, because obviously Google has a very interesting infrastructure and belief pattern. So it's been a fruitful relationship. So I'm happy to be here.
Thanks, Andy. OK. Time flies. It's been a year and a half.
Oh, OK.
Year and a half. So this raises an important question. Why is Google investing in Spinnaker? We've been working on it just about a year and a half. We started with one person. Now we have a quite sizable team. Half dozen or so engineers, program manager, product manager, and so on. So we are solidly invested in this effort. There are the obvious things. Our principles align. Putting these tools in the hands of the line developers, traceability, so who did what, when, where, why, and relying entirely on immutable infrastructure. So these things align, but there's more to it than that. Google is actively engaged in trying to take things that we do well internally, things we've been doing for a long time internally, and making them available externally. But it's not as simple as kind of hitting a giant red easy button and just making everything public. We can't flip any bit to just share all of our internal infrastructure. So where it makes sense and where it's reasonable, we're participating in open source efforts like this one to try to build on things that are out there that others have contributed to, and then get to a point where we have these sorts of internal capabilities available externally. In the case of Spinnaker, Netflix is like a recognized leader in the move to cloud, so it made a lot of sense for us to get involved with this. There are a few additional benefits which might not be immediately obvious. As we've developed Spinnaker, the Netflix guys have been sort of battle testing this thing internally. It's running in production all the time. So we can have a high degree of confidence that we're not making breaking changes because they're constantly testing this and applying a significant load to it. And B, it brings some sort of common sanity checks to any kinds of changes we propose. We're not just doing things sort of as we feel. We're discussing things, we're working out in the open, and then we all agree on changes as we make them. So, and the final thing worth mentioning is that the end result is a product for our users and our customers that doesn't rely on locking into our platform. I mean, it works with a significant set of cloud platforms, works very well with GCE. We'll talk more about integrations in the container world. But it supports multiple cloud platforms. You're not locked in. The capabilities are quite similar across all the different platforms. So let's leave that there. In 1 second, we're going to do a demo. OK, can I have the demo laptop, please? OK. I'll kick this off and then explain what we're seeing. OK, so this is a very simple web application. I'm going to make a simple change so we can see that change reflected, and then I'll explain in detail what's going on. OK, I changed one local file. I'm going to change a version number, and then I'll explain each step. I just want to give it time to get going. So. OK. So I have a local Git repo. It has a very simple web application in it. It's a typical hello world. Whatever parameter I pass to it, it'll echo it back and put hello in front of it. I made some change. I changed it from saying hello to saying hello GCP next, and then whatever name we pass to it. And then I did a local commit. It's a simple application. But we have Jenkins set up to poll every minute or two on that local Git repo, and when it notices any change was pushed to that branch, which in this case is just master, it'll kick off a build. And that build uses Gradle, packages up that application, and then produces a deb package and publishes it. And we'll look at each of these steps in more detail. This particular web application wasn't built by us. It was built by Kenzen Media, one of the other participants in the open source effort. So we can see Jenkins picked up that change and executed this build number 25. So at this point, can we have the presentation laptop, please? Okay. So this gives a kind of conceptual overview of the different components at work and also the workflow if we read it from left to right. So I'm going to start all the way at the left. I'll explain what I did so far and then what we're going to see. And I'm going to try to talk slowly, which I'm not great at. But the idea is I want to let the bake stage catch up. So starting at the left, I pushed a commit. I made a very simple change. We'll be able to see that change reflected in test and in production. And then I pushed that change to the local Git repo. Jenkins picked up the change through its polling, builds that web application, produces an OS package, in this case a Debian archive, and then publishes that to a repo. In practice, this can be something like bin tray, Artifactory. You have lots of choices. For the demo, I'm running a local aptly deb repo. This is the point where, like a typical continuous integration system like Jenkins and a continuous delivery framework like Spinnaker start to intersect. So we're right now where the blue shading begins to the left of that bake box. Okay, so the stuff in the blue shaded area, this represents a set of Spinnaker stages wired together in a Spinnaker pipeline. And this is where immutable infrastructure comes into play. So we pushed a change, our CI system picked it up, built it, ostensibly ran unit tests, although I don't have any, produced a deb package, published a deb package to some well-known repo. We have an option now. We could shell into our running systems, upgrade that application in place, and then we have the new version deployed. But that wouldn't be adhering to the immutable infrastructure principles. So what we're going to do instead is bake a static image, a hermetically sealed image, which should be familiar if you're familiar with Docker and containerization efforts. In this case, it's a VM image. We'll package up that image. Then we're going to deploy brand new cloud infrastructure, so cloud VMs with that image. We'll test those images. Once we decide they're happy, then we can disable or destroy the old servers. So why disable or destroy? If we're done with the old ones, we can just destroy them, right? The idea with disable is it's a traffic management operation. Instead of just destroying your old servers, just arrange it so that they don't take any more traffic from the load balancer sitting in front of them. This way, if something goes wrong, you can quickly go back. Okay? So make a change, push a change, build a deb package, produce a static machine image, deploy that static machine image into a test cluster, so a new set of VMs, wait until things are deemed healthy, and then disable or destroy the old server group. There's a little bit more to it. If you look at the top and bottom, so we mentioned it works in multiple cloud platforms. The test here is running against GCE, so that's really the top path. So we're producing a GCE machine image, and then we're deploying a GCE managed instance group. In Spinnaker terminology, we call these groups of homogeneous VMs server groups, but it's a managed instance group on GCE. If we were deploying an Amazon EC2 server group, it would be an auto-scaling group. Make sense? Okay. So this is what we're doing, right? Build the code, test it. When you're happy, push it through the stages into production. So we're taking all these first-class operations, this idea of a bake, a deploy, disable, destroy. We're taking all of these things, and then we're building a set of pipelines, and we're using that set of pipelines to have a system that takes source code changes and pushes them all the way through to production in a disciplined way and leaves open the possibility of doing a rollback very easily and quickly. Okay? So we roughly describe the first pipeline. So we bake, deploy, and in this case, if you're just doing a test, you can do something like a destroy. You're not going to do a rollback in a test cluster. One thing worth noting here, we mentioned, we don't have it in mind to rebuild everything from scratch. We're trying to rely on existing open source efforts where it makes sense and build on things that we consider the best of breed. The bakery relies entirely on Packer from HashiCorp. We built a web service around it, but basically it's a wrapper around Packer that understands naming conventions and versioning and things that are Spinnaker specific, but then delegates the actual work of producing those machine images to Packer. So we didn't reinvent baking machine images. We're just wrapping it in something that makes it a proper Spinnaker microservice and introduces versioning and all the other things we need for it to behave properly. Okay? So once that's done, it's going to trigger another pipeline. And the triggering bit is interesting. If you look all the way at the left, you see that sort of Jenkins guy, and there's a picture from Docker. The idea is you can kick off pipelines with a choice of triggers. There are cron-based triggers and other things. But once that pipeline completes, we want another pipeline to kick off. So that's a pipeline trigger. So the first one was a code push. That pipeline completes successfully. Then we have a pipeline trigger to kick off this validation pipeline. For the purposes of the demo, the pipeline that does validation does nothing other than have a manual judgment stage that says, validate everything's working. And then we'll go and click, yep, everything's good. Once that pipeline completes successfully, we have one final pipeline. And this is the promotion pipeline. And this is where it really gets kind of interesting. So what we've done to this point is push a code change via a new deb package onto a new set of machines into testing. Once we're happy with that image, and remember, it's not the servers we're testing, it's the image. Right? Once we're happy that the tests have passed successfully, we want to deploy that exact same image into production. We don't want to produce a new image. We don't want to reinstall that deb package. We don't want to open ourselves up to the risk that one of the systems we depend on has maybe increased its version and we get a later version that has some protocol switched off by default. That's Cassandra. So we don't want to open ourselves up to that. We want to push that image that we've tested into the production cluster. Okay? So at that point, instead of a bake stage, we use a find image stage. And you give it coordinates. You say, go to this cluster, find the latest or the largest server group, whatever makes sense for your deployment, gather those image details, and make them available in the context of that pipeline. So then any downstream deploy uses that image for its deployment. And finally, if you look at the end of that last deployment, we have a deployment strategy. So this is a blue-green. The Netflix guys with patriotism call these red-black deployments. Most people call these blue-green. So what it's going to do is not destroy the old server group. We said in testing, fine, we'll get rid of the old server group. No big deal. But in production, we're just going to make it so that the older server group, the older version of the software deployed on the old VMs, just doesn't take any more traffic. Still exists, we don't destroy it, but it gets deregistered from its load balancers. And then if something goes wrong, we can quickly roll back. All right. Can I have the demo laptop, please? OK. We mentioned the 3 pipelines. So bake and deploy to test is the top one. The middle one is validate test. And the last one is promote to production. So this top pipeline is executing. So we had the bake stage. And there's the usual attributes you'd expect, what distro to use. It describes what package is being installed, what cloud platform is being targeted. And that completed successfully, took about 4 minutes. Then we had a deploy operation. Could render better, but resolution's a little weird. So we're deploying that image that we baked in the bake stage into the test cluster. So again, you just give it coordinates. In this case, it's GCP next-test is the test cluster. And then following that is a destroy operation. And what the destroy operation will do in this case is determine the target server group based on the coordinates, which will be just the previous server group or the older version, and then it destroys it. And if we take a look at the clusters view, and this is very much like what Andy showed, only instead of 600 or 1,000 VMs in each server group, we really went for it and have 1 in each server group. So I have no backup video, so I'm playing it safe. So this is the test cluster on the bottom. And if we look here, this is the newly deployed server group. And when you click on any of these server groups, you can drill down into the details. And where it gets very interesting is you start to see the image information. This is the image that's under test. Okay? That's the image that was produced by that bake stage. You can see it in the execution details of the bake stage. And that's the image that we push into the test cluster. So we now have a new server group. And you see the old server group disappeared while I was talking. So that was that destroy stage. Okay? The idea is we would test this. So one thing we can do to test this, we can click on its load balancer, capture the DNS name or the IP address of the load balancer. And that's the change we made. We made it say, hello from GCP Next. I don't know if that's legible. All right. If we look at the production cluster that's running above it, which is this one, and we do the same thing, I have them associated with different load balancers. So we click on the IP address for the production load balancer. It has the old style message. So it doesn't have that change. So ostensibly, I've done more testing than just click on that and put my name in. But we're still going to go to the manual judgment stage and said, yes, we validated it. We're happy with the behavior of that image under test. At this point, it's going to kick off one final pipeline, which is the promotion to production pipeline. And the first stage here is find image. And what this does is look at that cluster, which is the test cluster, and say, determine what image to use. And then it primes the context of the pipeline with that image. And this is important. When you configure a deploy stage within a pipeline, you don't put in image information. The image information comes from context. So if it's something that was triggered directly by a Jenkins job completing, the image that gets primed into the context is associated with, if you have a pipeline that's triggered from a Jenkins context and you have a bake, the bake produces an image using the artifacts produced from that Jenkins job, and then the deployment uses the image that was produced from the bake stage. So you never say use this image. When you have another pipeline that has a find image, it looks at an existing cluster, determines what image was deployed, and then primes the context with that image, and that can be used by downstream deployments. But it's important that you're never explicitly selecting an image by name to use in one of the pipelines. It's always from context. Okay, so while that's running, we'll go back here and we'll see what's going on. So prior to kicking off that final pipeline, we had 2 server groups in the production cluster. So we had 6 and 7. And 6 is now grayed out, so it's disabled. 7 is still enabled. 8 is coming online. So the server group exists, but has 0 VMs deployed. So it's still spinning up. And what it's going to do when it does this deployment, we said there's a deployment strategy, this blue-green deployment strategy. It's going to take the old server group, disable it so it doesn't take any more traffic, after the new one has already reported healthy. So deploy the new one, wait for it's healthy, disable the old one. So disassociate it from its load balancers. Then it'll do a bit of cleanup, and in this case, it'll make sure there are no more than 2 server groups deployed, so it'll go and destroy any old disabled server groups beyond the one that was immediately disabled. That all making sense? All right, so we'll let that run, and then go back to that. OK. All right, so we described immutable infrastructure. We described some of the capabilities of Spinnaker, some of these sort of first-class stages like bake, deploy, disable, destroy. There are the other things you'd expect like resize, enable. You can re-enable something. There's rollback. There's a host of capabilities. All the things you see available in the pipelines are really built on top of operations that are available in kind of an ad hoc form within the UI. So you can do troubleshooting. You can isolate VMs that aren't behaving and take them out of the group so they don't take further traffic. But the important thing to keep in mind is that these principles, while we've demonstrated them here so far with virtual machines, apply equally well to a world built on containers. So we've been hard at work, and we have now an integration with Kubernetes far enough along that I can demonstrate it here live. And again, no backup video, so it could get real exciting. But the integration's in quite solid shape. Everything I'm showing here is checked in, so I'm running what's committed at head, basically. So anything we're doing here, you can easily try out on your own. So I'll kick off the demo, and then I'll explain a bit more about the Kubernetes integration, because I don't want to run out of time. So I'll just get it going, and then we'll. So this is another simple Hello World application. This time it's in Go instead of Java or Groovy. So I'm changing a version number, and then I have an endpoint that'll let me see the version when it comes up. So we'll be able to determine that we actually got the correct version. OK. So I changed one simple file. Yep. Yep. So I went into this very simple Go application. I changed the version string that'll be returned from /version. And then I basically tagged and pushed that container image to a Docker registry. So in this case, I'm running using Google Container Registry. It's like a hosted Docker registry. Makes it easy to configure the credentials. But the important thing is that all I did was just tag it and push it. I didn't do anything else. The integration between Spinnaker and Kubernetes relies on a few different things. The first, you need a Kubernetes cluster. So in this case, as we get into the demo, it'll become clear, but we're running against Google Container Engine. It just makes it easy to set up. But any Kubernetes cluster that you have, whether it's on-prem or on AWS or using GKE, it'll work exactly the same. You just need a cluster endpoint and credentials to access it. So the integration needs a Kubernetes cluster, credentials to access it, and it needs to know where to pull images from. For that sample application, I'm using Google Container Registry, so I configured my Kubernetes account within Spinnaker to pull my Google Container Registry account. So it's just looking in those repositories. But what it's doing is polling at some interval, and anytime it sees a change to any image, it pumps an event into Spinnaker. And then if I have a pipeline configured to trigger from a change to any image in my container registry, it'll kick off that pipeline. And you can do the things you'd expect. You can make it listen for a specific tag or all tags. You can have it listen for changes to multiple images. All of that works quite well. In this case, we're keeping it simple. It's one image. It's all within my same Google Cloud Platform account, and I'm relying on the hosted services to make it a bit easier. So I mentioned there are different kinds of triggers. We'll dig into the pipeline here. OK. So this is a Docker trigger. It basically says any push to a Docker registry, and that's the registry to pull. That involves a change to that repository. In this case, I didn't specify a tag, so any tagged image will kick off this pipeline. If it detects that change, it kicks off the pipeline. So what does the pipeline look like? It's quite simple. There's a deploy stage. And we didn't look at this yet. I can show you what the deploy wizard looks like. This looks pretty similar from cloud platform to cloud platform. The details differ a little bit, but the overall flow is quite consistent between platforms. It's not, it's not a pure abstraction where every platform has to fit the exact shape, but the experience is consistent from platform to platform. So there's all the details you'd expect. You have to choose what containers you want to deploy. And it's just polling the registry. So whatever's available in your registry is what's available in the UI. Okay? You can associate it with load balancers. Now, all of these constructs map to the proper Kubernetes construct. So load balancers map to services. The server groups, we explained on GCE, these are managed instance groups. On AWS, these are auto-scaling groups. On Kubernetes, these are replication controllers. And whereas on the different virtual machine integrations we described, each server group deploys VMs that really contain a single instance, the server groups in this case are replication controllers deploying pods that can contain multiple containers. So this demo, we're just deploying one. But you can deploy as many containers as makes sense for your pod. Okay? And so on, and you can specify all the resource settings, environment variables, mount volumes, all the things you'd expect to be able to do, you can do. The nice thing about this is that we're providing a consistent experience across platforms, and we're hiding a lot of the complexity. You can always drill down, get to all the details, but you don't have to bury yourself in all that complexity. So your sort of day-to-day workflow as you deploy your changes into production is made quite a bit easier. So we have a deploy stage, and then we have a disable server group stage. And in this case, well, Kubernetes relies on selectors and labels, so that's what we're doing. Okay? We're not disassociating it from a load balancer. We're changing the labels such that the services selectors don't pick up those replication controllers. And then, again, a manual judgment stage. And I've been just as thorough with my testing as I was before. It says validate it. I validate the test quotation. So same thing, and we'll just click OK when we get to it. And then the last thing is a resize. So let's go back. Let's see how far it got. So it did the deploy. It did the disable. And now it's waiting for my judgment. I have very good judgment. I'll say it worked great. Now it's doing a resize. So let's take a look at the cluster view while this kicks off. So this is the cluster, and I'll explain a bit more about what's on the screen in a second, because there's one other thing I want to call out. But you can see that grayed out cluster at the bottom. That was deployed previously. It was disabled, so it's grayed out. The one that's resizing now, when it was first deployed, it had one container. We said test it. Once we're happy with the test, we'll scale it up. In this case, I scaled it to 400 containers, and it'll take a minute or so, and then you'll see they'll all turn green. But there's one other interesting thing on this page. So at the bottom, we have a Kubernetes cluster. In the middle, we have a GCE cluster. And then at the top, we have an Amazon cluster. And they all look quite similar. All the health checking works quite similarly. You get sort of the high-level view looks about the same. But then as you start to drill down, you can see there are differences. And you can get to the details if you want. So you can see, obviously, the zones are different. And you can see the VPC information and so on. And there are context menus and things everywhere that make sense for the selected resource types. Okay, so that should be deploying. So this is cruising right along. Okay, so it's done. The Kubernetes stuff works very well. It's very fast, kind of snappy. And one nice thing is we expose the YAML everywhere. So if you actually want to see the YAML that's backing all these resources, it's quite easy to drill down on any one of them. All right. Okay, if I could have the presentation laptop, please. Okay, so you can see how it maps, right? We covered the GCE one, and then this is how the Kubernetes integration maps down to the key Kubernetes resources. So we'll come back to the triggering in a second. But you're deploying Docker images or container images in this case. You're not deploying groups of VMs. You're just deploying replication controllers. And instead of containing VMs, they contain pods. So and pods can contain multiple containers. We support all of that throughout. Okay? And the same thing, you can, again, apply those same first-class operations. So you can do a red-black deployment or a blue-green deployment on Kubernetes resources. And the triggering is just what we said. Instead of looking for necessarily a Jenkins job to complete, you can poll on something like Docker Hub, and when you see a change pushed, you kick off your job. Clicker. OK, so status. This was open source November 16th, 2015. Quite comprehensive support for Amazon's EC2 and for Google Compute Engine. Pivotal has been adding Cloud Foundry support. It's quite far along. Microsoft Azure has a team working on it. We meet weekly. We're all working out in the open together. It's been pretty interesting, trying to learn from each other, and you see kind of the same struggles as we all come up to speed. So, but they're coming along, and they have also some sort of developer conference coming up where they're going to be presenting Spinnaker as well. So again, it supports a bunch of different cloud platforms. So the Kubernetes support, everything I showed today is checked in. I'm working basically from head. These are from the published Debian packages. I just built an image using the hosted scripts. This is being used in production at Netflix. There are quite a few other companies using it. We have some internal folks at Google using it as well. And we have a thriving open source community. There's a Slack chat room that has, it must be 1,000 or close to 1,000 users now in the general channel there. We have some tags on Stack Overflow, and obviously there are, I don't know, 8 or 9 or 10 or more GitHub repos that host the various services and all the umbrella projects that control it all. If you want to give it a shot, on the Google Cloud Launcher, we have a quite easy to use solution. It's a couple of clicks, no configuration. You'll be up and running within your GCP project. And there are tutorials on our spinnaker.io page and on our Cloud Solutions page that will sort of point you in the right direction. We'll all be available out in the playground. We're not sure where that is, but they said to say that after this. And Andy brought some of his guys from Netflix, so direct all the hard questions to them. And thank you all for coming. Appreciate it.